All right, here we go.
This is called the Van de Graaff generator. It's named after a person by the name of Robert J. All right, we be learning this stuff. All right. Now, what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice I am, notice that I am keeping this closer to the dome than my head. Guess why? I don't want to put my head closer than this, all right? Now let me show you that that does charge. Let's try this, gang.
Ooh, I want you guys to hypothesize before you see this. There's got a bunch of individual pie plates, right? A bunch of individual pie plates. They're all metal, but they're all individual. Okay, he's gonna stack them on top there. Remember, that's a huge positive charge. Do you think that all those individual pie plates are going to become positively charged? If that happens, then what's gonna happen next? Gonna explode. Right. Like charges repel.
And so the flow of current is proportional to voltage difference. Not how much voltage, but how much voltage in one place compared to the other. Think of voltage as a pressure. Huh? So it's proportional to voltage difference. Proportional to. So the more voltage difference, the more. Hey, imagine I have a pipe right here filled with water. Okay, see that water-filled pipe? I have a piston over here, and I have a piston here. And I push with a certain pressure, maybe 5 units. I push with the same pressure here, 5 units. Which way does the water flow? I mean, the water ain't gonna flow at all. I say, yeah, I got under pressure. And you say, yeah, but there's no pressure difference. How about I push here with 5? And I push over here with 3. What does the water do, gang? What does the water do? The water flows, okay? And similarly, if you take a piece of wire and you put a pressure difference across the wire, and I can do that here. Here's a lamp, okay? This is a 12-volt battery. One end is 12 volts higher than the other. If I touch here and touch here, no light. If I touch here and touch here, no light. There's 12 volts, 12 volts. Why no light? Check your neighbor, why no light? Let's try the other side. No light, still no light. Why? How come? But I got 0 volts over here. Oh, over here I got 12 volts. There's no difference. You gotta have a difference. Look at how I go like this. Ought to be, huh? What's the voltage difference across the lamp now? 12. So if you got a voltage difference, you get a current. It kind of makes sense. This is not counterintuitive. The more voltage difference you have, the more current you're going to have through a conductor. And this is a conductor. It's a piece of wire made out of copper with electrons can flow all through there, gang. So I have a conducting path with a voltage difference. No voltage difference, no current at all. Voltage difference for a current. Make sense? When you touch a wire, a lot of times people touch a wire and they get, they can't let go. You know what I can't let go? People, oh, they attracted to the electric. No, he ain't attracted. Contraction. Remember the biology experiment you do, the frog's legs, the frog leg like that, and you come over and you touch it like that. The frog is dead, honey. And it's still going like that. It turns out it's an electrical. Can you guys do that? Try it. I hope you can. You know what you guys are doing? You are sending electrical impulses down your hand. It's electrical impulses to do that. And it contracts. So what happened when you touch the wire? It's not that you attract, it's that your fingers contract. So he told us that electrician types always, if they're fooling around, they touch like this. You touch that, contract, you pull away, see? You're okay. But you don't want to go like that. You know what I'm saying? Practical stuff. Hey, why is it that you see birds on high tension wires, bare wires, and you see the bird come down and you grab on a foot and stand on one foot and he's on the wire. And the bird doesn't get fried. The bird's okay. Now what happened? The bird reached down and put the other foot on the same wire. What happened to the bird then? Begin with N and with nothing. Try it. Nothing. He said, bird's okay. Look, hey man, the bird's 100,000 volts. Is the bird all right? The bird is all right. Because you get 100. What's the voltage difference across the bird? Zilch. Zilch. This relationship, current proportional to voltage difference, becomes an exact equation when I include the idea of resistance. If you have a humongous resistance, even for a big voltage difference, the current will be very small. So how much current flows through things has to do with two ideas, gang. What's the voltage difference across the ends of the conductor? And what's the resistance that that conductor offers to a current flow to begin with? And that usually has to do with the geometry and the material of the conductor. Like a great big fat piece of copper has less resistance than a little skinny piece of copper. Just like a great big humongous pipe will have less resistance to the flow of water than a little skinny pipe, yeah? And how about a lamp like this? This copper right here, it's relatively thick, but it's very, very thin in there where the filament is. Guess where most of the resistance is across these two leads? Begins with FIL, filament. In that filament is most of the resistance. And guess where most of the energy is dissipated going from here to here when I touch it across the battery? Right in the filament. In fact, the filament reacts so bad, it turns white hot with heat. Look at that, it's glowing. And there's your lamp. Isn't that nice? So we measure current in amperes, amps, okay? And we measure voltage in volts, and we measure resistance in all together now. Ohms. Okay, there's an ohm, yeah, that's ohms. In fact, ohms are written like this. Greek letter omega, ohm. Voltage is written like this, V, and current is in amps. The unit is amps, and oftentimes we call current I. So we could say I equals V over R. And it's the old song and dance, gang, that if you know two of these things, you know the other. Like, for example, let's suppose I tell you the resistance of this little lamp is 1 ohm. And I put it across this 12-volt battery. There are people in this room besides Lee who can tell me how much current is flowing through the battery. And then there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance.
All right, so he says 1 ohm resistance. He's got 12-volt difference. So how many amps would that be? Yeah, 12 amps, right? Yeah, you guys say 12 amps, right? All right, let's see if I can. Right. Yeah, you guys know in physics, the variable and the unit we use the different characters for, right? And here's one weird sort of exception is voltage, right? So capital V could stand for voltage, like as a variable, but it could also stand for volts as a unit. So that could be like the same character, right? But that's like the only variable unit that's like that, right? Like current I is measured in amps A, right? Or resistance measured in ohms, right? A lot of textbooks, instead of using capital V for voltage, they might use delta V for potential difference, or sometimes the Greek letter epsilon looks like a little loopy E. I think some of my posters I put a little epsilon too, so you can see that too.
People in this room besides Lee who can tell me how much current is flowing through the battery. And then there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance, 12 volts across the battery. What's the answer again? 12, and that's 12 amps. That's Ohm's law.
All right, so next, there was a Paul Hewitt one where he talks about alternating current, but where, I think it's just easier to use this one. Where's, can I repeat this? Can I loop this thing? Where's the loop button? What is this?
Oh,
Repeat. Yeah, let's try this. All right, here we go. All right, so there's actually two kinds of current you can set off, direct current and alternating current. And each one is useful for different purposes. Anything that you put a battery in is going to be direct current. So if you have a watch, those calculators on your desk, cell phones, right? Anything with a battery in it, right? What's going on there is that there's a physical movement of electrons. Again, it's really slow, but no, they go from the negative terminal to the positive terminal. So they actually flow opposite of what these red dots are doing, the electrons do, right? But what this diagram is showing is the flow of positive charge, which is how it's been defined for hundreds of years. So they're showing the opposite of what the electrons are doing, right? Right. So, okay, right. But how electricity is sent over the power grid is actually alternating current, which is actually not hard to make. All you do is you put a rotating magnet next to a coil of wires, and as that magnet rotates, it'll go from north south. It'll naturally make it alternate. So the electrons where the charge is just alternating. It's just going back and forth. Now, the reason for this is that it's a lot more efficient to send alternating current over power grid. It's easier to step up and step down the voltage with a transformer using inductive coupling. We'll talk about in the near future. Right, so you might have like tens of thousands of volts going across a power line, but you need to step that down to like 240 or 120 volts by the time it like ready to enter a building or something like that. And then if you plug anything to these outlets in this room, it's 120 volts, alternating current. So it's like sloshing back and forth. Okay. So there's energy transfer, but there's no net movement of electrons with alternating current. Do you guys know the frequency rate in the United States for alternating current? Right? Because you have to design your appliances for some particular frequency standard. Right? And all of North America, does anybody know? Right, 60 hertz. Yeah, 60 hertz. Yeah, 60 hertz standard. If you go over to Europe, none of your American appliances will work because they're on a 50 hertz standard. Right. So those are the two main standards for alternating current, either 50 or 60 hertz, and we're on a 60 hertz standard. All right. There you go. Let's do one more. Take this off loop here. Do that. Okay. So one more Paul Hewitt. I'll do it. All right.
I'm going to hook this up like that. And lo and behold, it lights. What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room, and I could take these two leads and I could bring them to the other side of campus. And over on the other side of campus, I could go like this, and I'd say, what's the voltage across the leads, gang? And what would you guys say? 12. And it would light up over there. In fact, what do you think a wire is? A wire is just two leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it and you're on. See, it's like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? Let's suppose I go like this, gang. Let's suppose I put another lamp in here.
All right, so he's going to do a bunch here. This was a little bit longer. Pay real close attention. He does a bunch of things with these bulbs. He's about to put one bulb after another, which is called in series. You guys see the poster up here that says in series, right? So the electricity has to go through one bulb and then through the other sequentially, like one after another, right? Now, what do you guys think is going to happen to the brightness of the bulbs when he puts one after another? Let me see, show of hands. How many guys say that the brightness is going to stay the same? You guys remember how bright one bulb was, right? Right. And how many guys think it's going to get dimmer? All right, so I'm seeing some votes on each one. Let's see how it's that.
I'll put another lamp in series. Series. I'm using your word, gang. Series. Huh? There's one right after the other. I should have asked you before I did it. Will a lamp glow brighter or less bright? And you guys would have said anyway, it's less bright. And I say, what's the voltage across the two lamps? And you guys would have said, what's the voltage across one lamp? And you guys would say, yeah, feels good, feels good. 6. 6 and 6 is what? 12. That's right, too. If you take the 6 volts across this one ohm, what's the current in there?
Oh, okay. So he's digging into the circuit now. He's got a real basic circuit. It's just got 2 resistors on it, right? 2 bulbs. Okay, but he's approaching this from a micro point of view. So he's digging into it. So notice what he said happens to the voltage, right? We've got 12 volts over here and 0 volts over here. So there's a 12 volt difference, right? And it stepped down 6 volts across this one and then 6 this one. So it drops 6 volts and 6 volts, right? Remember how a voltage is sort of analogous to pressure, right? You could also think of that kind of analogous to cliff height. If you have like a waterfall going over a cliff, or maybe like a dam. How about that? Like how deep is the dam? Like the deeper the dam, the more pressure, right? So if you had a 12-meter tall cliff, it's like it drops down 6 meters followed by another 6 meters, right? You guys can see that too, right? So voltage is analogous to pressure. You can also think of that like a waterfall height, right? Right. Okay. So we said a 6-volt drop across this one, 6-volt drop, right? And it's still 1 ohm of resistance. So what's the current through this guy? How many amps? What is 6-volt drop acting on 1 ohm resistance? That 6 amps, right? So that's 6 amps, right? Okay. Now I might approach this from a macro point of view. That's what I tend to do, right? So I might do this from the point of view of the battery. And from the point of view of the battery is saying, well, there was 1 ohm resistor, but now there's 2 in series. So you just very simply add those. That's 2 ohms resistance total from the battery. The battery just felt the resistance double, right? So guys, what is 12 volts acting on 2 ohms of resistance? What's 12 over 2? That's still 6 amps, right? You get the same result, just from different points of view. He's doing micro, I'm doing macro, but it still gets you to 6 amps, right? Right. Now, amps, remember that's like flow rate, think gallons per minute, cubic meters per second. Flow rate is also sort of analogous to traffic flow. What if this battery represented a parking garage? It was full of cars, right? And these cars want to get on these streets and drive around town and go back to the parking garage, right? So they have a closed circuit so they can drive all the way around town. And they were originally looking at like 1 stoplight. Okay, so there were 12 cars that went out driving around town. But now they're looking out and they say, see 2 stoplights? I don't know. And then a bunch of them just like don't drive on the road. So now you're down to 6 amps. That's kind of like 6 cars, right? But don't all 6 cars have to go through both stoplights? Because there's only one path for them to go through. You see that? So all 6 amps go through everything because it's all just one series circuit.
Well, we got to go through that again. If I get 6 volts across there and a resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series, how many amps right through this little point right here? How many amperes? How many amperes through a point right here? 6. And how many amperes flew through the battery? 6. 6. 6. 6. 6. 6. All the way along. How many amperes up here? None. This is not part of the circuit. My circuit's right through there. See what I'm saying? The current flowing through the circuit. And the circuit now has twice as much resistance as before. If it quite got twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do. And everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we got? It sure is dimmer.
So now he's got 3 bulbs in series, one after another, right? And if each one individually is 1 ohm, because what's the total resistance? 3 ohms, right? So just very simply, you add them up. Right? Now that'll change later, but in series, you just add them up, right? So let's do a macro point of view, right? So the battery says I'm supplying a 12-volt voltage difference, right? 12 volts here, 0 volts here. It's 12-volt difference, right? Acting on 3 ohms total resistance, how many amps of current is that? 4 amps, right? 12 on 3, that's 4 amps, right? It's 4 amps. And again, there's only one path for the electricity to flow through, right? So it's kind of like having one street that loops around back to the parking garage. There's 3 stoplights now, but it's only one street. So now I got 4 cars leaving the parking garage, driving all the way around town, and 4 cars go back through, back to the parking garage, back to the battery, right? So 4 amps.
Let me ask you guys a question. What's the voltage across the whole system? 12. Okay. How much resistance we got now compared to before? 3 times the resistance. How much is the current now compared to the 1? 1/3. Ain't that neat? So now you got 1/3 of an amp. Huh?
He meant to say 1/3 of the original, which would be 1/3 of 12 would be 4 amps. Right?
What's the voltage across one of these things? 1/3 of 12. 4. Okay. Is 4 1 ohm? Do I have it right? Did I make a mistake? Did I make a mistake, gang? I never make mistakes. But we have 4 volts across here. Okay, yes. 1 ohm, so we have 4 amps. What's going through here? 4. Before it was 6, and first of all, it was 12. So the current's getting less and less because the resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series, but in parallel, like the rungs of a ladder, parallel. I'm going to hook.
What do you guys think is going to happen to the brightness of the bulb now when he hooks it in parallel?
Look this. What's gonna happen to the brightness of that lamp when I connect this? How many say nothing? My people, that's right. Because let me ask you a question. What's the voltage across this lamp? What's the voltage across this lamp? What's the resistance of this? So what's the current through this? 12. 12.
12 amps, right?
What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12. 12 amps, 12 amps, 12 amps. To be amps, volts, I get mixed up again. The voltage is the pressure supplied by the battery, 12. There's 12 right through across these, from these two prongs, yeah? And I pick up the 12, 12, 12. The battery gonna wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here? 12. It's like automobiles driving from a garage down here. And some of those automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay? How many through here? 12. How many through here? How many through here? Ah, what is it? Right, there's 24. Guess you get the 12 from here, and you get the 12 coming down this street. How many through here? 24. How many through here? You guys are on 12. How many through here? 36. How many through the battery? Who's getting tired? The battery. The battery.
So every time he attaches on a new light bulb, another resistor in parallel, like rungs up a ladder, it's kind of like building a new road for traffic to drive along. Even though you might say, "Oh, there's even more stoplights being built." Yeah, but it's new roads being built, right? So now even more cars can travel. Or another way to think of it is that every time he adds on another resistor in parallel, what happens to the overall resistance? Does it go up or go down? If it goes down, it gets less and less, right? Because it's like opening new ways for the traffic to flow.
More energy going out, no, more power going out. You get it? Okay? Think about these ideas.
Sure, but
I'm gonna hook this up like that. And lo and behold, it lights.
Oh.
What's the volt?
oh, I don't think I was sure. Am I sharing my screen? I don't know. I think I am. Okay. Yeah, thanks. Check that later. All right. All right. So here, do a preview tomorrow. So seeing resistors in series, if they're one after another, you can just add up the resistances and get the total resistance. Okay. Now, if they're like rungs of a ladder, like parallel, that's the last thing you guys saw. Okay. You have to do this type math bit. If you add the reciprocals, you get the reciprocal of the total. Right. Or if you only have two at a time, you can only do this with two at a time. You can do product over sum, and it works out to be the same thing. Like if I just had like these two like this, or just those two, if I just focus on those two, you do product over sum, right? Which means that every time you add on a new resistor in parallel, it actually decreases the total resistance, okay? So we'll look more of that tomorrow, but I know bell's gonna ring here in about 10 seconds. So let's start pause point today.